This conference will now be recorded.
On behalf of C.B.Patel Computer College and J.N.M.Patel Science College, managed by Kantha Vibhag Navamina Mandal, Surat. Welcome back again, you all participants, in the second day of 2 days webinar. Before starting the session, I would like to announce some instruction. All the participants, please turn off your mic and video during the session. If you have any query or question, you can ask your question in comment box or chat box. So please do not switch on your mic and video until the end of the session, so that we can able to run the session smoothly. Today's respected resource person, Mr. Vishwas Khare, is with us, who is going to deliver his talk on solution of ODE using Lie symmetry and open source Sagemath algorithm. Mr. Vishwas Khare is an assistant professor and head Department of Mathematics in SSR College of Arts, Commerce and Science, Silvassa. He is MSc, MPhil and NET, and currently doing his research work from VNHU Surat under the guidance of Dr. M.G. Timol. He is having more than 15 years of teaching experience in degree college. He has attended many FDPS, national and international conferences and presented research paper over there. He has prepared many video lectures for students on various topics which are available on YouTube. I heartily welcome you, sir, in the second day of webinar as a resource person, and thank you very much for being with us. Now, sir, you can start your talk. Over to you, sir.
Okay, am I audible?
Yes, yes.
Am I audible?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Yes, sir. You are audible.
Yes.
Good morning, all of, good morning, all of you. I'm Vishwas Khare from SSR College, Silvassa. In today's presentation, I will talk about solution of ODE using Lie symmetry and open source Sagemath algorithm. To solve a first order ODE, one needs to find whether given ODE is linear equation, Bernoulli equation, homogeneous equation, exact equation, or in any standard form. If the given ODE does not fit in any standard form, then to find exact solution of ODE is not easy, and one has to satisfy with approximate solutions. Similarly, to solve a differential equation of second order, there are techniques that reduce the order of second order differential equation by 1, provided it is in standard form and one of the solution of the ODE is known. Norwegian mathematician Sophus Lie introduced the technique of solving differential equation known as symmetry method for differential equation. Using symmetry methods, we can find exact solution of many differential equations which cannot be found by established usual method. In this method, to solve a given ODE, we find the group of transformation associated with or admitted by ODE. In particular, we find the infinitesimal transformations associated with the group of transformation of an ODE. Using infinitesimals, we find canonical coordinates which transform the first order ODE in variable separable form, which can be solved using integration. For second order ODE, the transformed equation becomes ODE in first order. Now let me talk about Sagemath software. Sagemath is an open source mathematics computing environment that includes mathematics in textual form and displays it in either textual form or traditional form. Sagemath is written in the powerful and very popular Python programming language and the mathematics-oriented programming language. To make the computation easy, we have developed an algorithm in Sagemath for finding, determining equation for infinitesimals, for finding values of canonical coordinates R and S, and converting the given ODE in variables R and S. Now, what is symmetry of planar object? The symmetry of planar object is a transformation that leaves that object unchanged or invariant. For example, consider the equilateral triangle with the vertices labeled as 1, 3. If we rotate this triangle with angle 0, 2 pi by 3 or 4 pi by 3, or reflect it through any bisection axis passing through vertex 1, 2 or 3, the triangle remains invariant. Of course, the position of 1, 2, 3 will be changed, but the triangle will remain invariant. Thus, equilateral triangle has 6 symmetries. Now, consider the unit circle x square plus y square is equal to 1 and the transformation x epsilon, which takes xy points to x star y star point, where x star is given by x cos epsilon minus y sin epsilon, and y star is x sin epsilon plus y cos epsilon, for each epsilon belongs to minus pi to pi. Now, if we rotate the circle with an angle epsilon, it remains invariant. Here, the circle has infinite set of symmetries. That is, there are planar objects which are having, some planar objects have finite number of symmetries and some are having infinite set of symmetries. Also, we note that x star square plus y star square is equal to 1. Now, let us consider symmetry of ODEs. Consider a first order ordinary differential equation dy by dx is equal to wxy. We say transformation x star, that's capital X depending on the point x, y, epsilon, y star, capital Y depending on x, y, and epsilon, is associated with the if E, we say ODE is invariant under the transformation dy star by dx star, or when dy. For example, the transformation x star is equal to e to the power epsilon x, y star is equal to e to the power minus epsilon y is associated with ODE dy by dx is equal to xy cube, because when you compute dy star by dx star, it is same as x star y star cube when dy by dx is equal to xy cube. That is, the equation remains changed. The equation remains same even if we change the variables. This concept can be extended to nth order ODE also. To solve an ODE, we try to find the symmetry associated with ODE, which is not an easy task. Now let us see an important observation. Suppose the ODE dy by dx is equal to wxy is invariant under transformation x star is equal to x, y star is equal to y plus epsilon, which is translation in bidirection. Then we can show that the partial derivative of w with respect of y is equal to 0. Therefore, the most general ODE, which is invariant under 1, is of the form dy by dx is equal to wx, which can be solved easily, and the general solution is given by y is equal to integration of wx dx plus c. In symmetry method, we find new coordinates such that the converted ODE is invariant under translation in new coordinates. These new coordinates, later on, we will call them canonical coordinates. Now let us see this concept in detail. Group of transformation. Let x is equal to x1, x2, xn be point belongs to region T, which is a subset of Rn. The set of transformation x star, that's capital X, depending on the point x and epsilon, defined for each x in T, depending on parameter epsilon, lying in the set as contained in R, with phi, defining a law of composition of parameter epsilon and delta in S forms a group of transformation on D if number one, for each parameter epsilon in S, the transformations are one-to-one onto D. In particular, the transform point x star lies in D. Second, S with the law of composition phi forms a group G. Third, x star is equal to x when epsilon is equal to E. That is identity. That is x e is equal to x. Fourth, x star is equal to x epsilon, and if x double star is equal to x star delta, then x double star is equal to x phi. That is, if we transform x to x star is transformed to x double star, and there should be a transformation which transform x to directly x double star. Now a group of transformation, which I described in the last slide, defines a one parameter Lie group of transformation if in addition to satisfy axioms 1 and 4 given in the above definition, it satisfies if epsilon is a continuous parameter, that is S is an interval in R. Without loss of generality, we can take epsilon is equal to 0 corresponding to the identity element E. 6. X is infinitely differentiable with respect to x in D, an analytical function of epsilon in S. 7. Phi is an analytic function of epsilon and delta, and epsilon and delta belongs to S. Now let us take some examples of one parameter Lie group of transformation. First example is group of translation in the plane, where x star is defined as x, y star is defined as phi plus epsilon, where epsilon belongs to R. Second, group of rotation in the plane, where x star is defined as x cos epsilon minus phi sin epsilon, y star is defined as x sin epsilon plus phi cos epsilon. Third, group of scaling in the plane. Here, the x star is defined as 1 plus epsilon into x, and y star is defined as 1 plus epsilon whole square y, where minus 1 less than epsilon less than infinity. Now let us talk about infinitesimal transformation. What is infinitesimal transformation? Consider a one parameter Lie group of transformation. X star is equal to x epsilon with identity epsilon is equal to 0 and law of composition phi. Expanding this capital X about epsilon is equal to 0, we get for some neighborhood epsilon is equal to 0, x star is equal to small x plus epsilon, partial derivative of x with respect to epsilon at epsilon is equal to 0 plus term of order epsilon square. Let xi x is equal to partial derivative of x with respect to epsilon at epsilon is equal to 0. Then the transformation x plus xi x is called the infinitesimal transformation of Lie group of transformation x star is equal to x epsilon. That is, we are associating infinitesimal transformation with the given Lie group of transformation. And the components of xi x are called the infinitesimals of the group x star is equal to capital X depending on point x and epsilon. For example, consider the group of translation in the plane x star is equal to x and y star is equal to y plus epsilon, where epsilon belongs to R. In this case, the infinitesimals associated with the group are given by xi xy, that is, we find the partial derivative of x with respect to epsilon and epsilon is equal to 0. Clearly, its value is 0. And eta xy, that is partial derivative of y star, which is 5 plus epsilon with respect to epsilon at epsilon is equal to 0. And clearly, its value is 1. Conversely, we can find the group of transformation from the values of infinitesimal associated with the group. Now let us one more terminology, infinitesimal generator. The infinitesimal generator of the Lie of the one parameter Lie group of transformation x star x depending on point x and epsilon is the operator x bold X. You can use any other symbol T also for the transformation. I will use this symbol, which is summation I is equal to 1 to n xi x into del pi and del xi. For example, for the group of translation in the plane x star is equal to x and y star is equal to y plus epsilon, epsilon belongs to r, we have calculated in last slide that xi is equal to 0 and eta is equal to 1. Therefore, this capital X becomes 0 times del by del x plus 1 times del by del y, which is del by del y. Now the next terminology is canonical coordinates. The theorem says that for any Lie group of transformation x star, x epsilon, there exists a set of coordinates y, depending on y1, y2, yn is the point. All canonical coordinates such that x star is equal to x depending on x and epsilon is equal to y star is equal to y, I is equal to 1, 2, n minus 1, y n star is equal to yn plus epsilon. And in terms of set of canonical coordinates, the infinitesimal generator becomes capital Y is equal to partial derivative del by del y. The canonical coordinates y for I is equal to 1, 2, n minus 1 can be found by solving x minus x is equal to 0 and y and x is obtained by solving x, y and x is equal to 0. This theorem gives the guarantee that is whenever we are having a Lie group of transformation, we can find the canonical coordinates, which will be helpful in transforming the first order ODE in variable separable form, and in case of second order ODE, it reduces the order by 1. Now let us see this geometrically in variance of nth order ODE. The general solution of an ordinary differential equation is represented geometrically by a family of curves. A group of transformation is said to be admitted by a differential equation if it maps any solution curve into another solution curve. In particular, a group of transformation admitted by a differential equation must leave a family of solution curve invariant. Consider an nth order ODE written in the solved form y is equal to n x y y1 up to yn minus 1, where yk is denoted kth order derivative of y with respect to x. K is equal to 1 to n. The ODE2 defines a surface in x, y, y1, yn space. Definition: the one parameter Lie group of transformation x star is equal to capital X depending on the point x, y, and epsilon. Y star is equal to capital Y depending on the point x, y, and epsilon. Because we are talking about ODE, so we are taking only points x, y. Leaves ODE2 invariant, or we say is admitted by the ODE2 if and only its nth extension defined by x star is equal to capital X depending on x, y, epsilon, y star is equal to capital Y depending on x, y, epsilon, yk star, that is capital Yk defined by total derivative of yk minus 1 depending on divided by total derivative of x for k is equal to n, leaves the surface 2 invariant, where the d by dk is total derivative operator given by d by dx is equal to partial derivative d by dx plus y1, partial derivative with respect to y, y2 partial derivative with respect to y1, yn plus 1 partial derivative with respect to y, and so on. Invariance of surface 2 under the nth extension of 3 means that any solution curve y is equal to theta x of 2 maps into some other solution curve y is equal to phi x epsilon of 2 under the action of the group 3. Now the next concept, infinitesimal criteria for invariance of ODE. This will be useful when we'll solve the ODEs. Practically, let x is equal to xi xy del by del x plus eta xy del by del y be the infinitesimal generator of the group x star is equal to capital X, xy epsilon, y star is equal to capital Y, xy epsilon, and let xn, that is xi del by del x plus eta del by del y, eta 1 del by del y1, eta n del by del yn be the nth extended infinitesimal generator of x, where nk is total derivative of eta k minus 1 minus phi k total derivative of xi, for k is equal to 1 to n, and eta 0 is same as eta xy. Then x star, which is equal to capital X depending on point x, y, epsilon, y star, that is capital Y, x, y, epsilon, is admitted by the differential equation y, which is written in solved form as f x, y, y1, yn minus 1. If and only xn, that is this operator, when it will operate on the differential equation yn minus f x, y1, yn minus 1 is equal to 0, when yn is equal to f x, y, y1 up to yn minus 1. This is called the linearized symmetry condition. This is very important condition. Using this, we find later on the infinite symmetry. On solving linearized symmetry condition, we obtain the values of infinite symmetries. Now let us in particular talk about first order ODE. For first order ODE, y1 is equal to f x, y. Linearized symmetry condition is given by x1 into y1 minus fxy is equal to 0 whenever y1 is equal to fxy. We have seen in the last slides for nth order ODE. This is in particular first order ODE, where x1 is given by xi xy del by del x, eta xy del by del y, plus eta 1 del by del y1, which is when you solve this, which is equivalent to eta x, that is partial derivative of eta with respect to x, plus eta y minus xi x into f minus xi y f square is equal to xi fx plus eta fy. Here fy represents partial derivative of f with respect to y. And similarly, fx represents partial derivative of f with respect to x. On solving, we get infinitesimal xi and eta. Now in finding, this is not easy to solve this equation in general. So what we do, in finding the infinitesimal, we try n tasks such as xi is equal to alpha x and eta is equal to beta xy plus gamma x etc. That is, we suppose that we want solution in the terms of xi is equal to alpha x. That is, we suppose that we want xi as a some function of x and eta as a some function of x into y and gamma x. Or we can take xi is equal to some function of y also. Now, once the infinitesimals are found, then using infinitesimals, we find canonical coordinates, which are very important for us, and that are as follows. If xi xy is not equal to 0, then the invariant canonical coordinate r is found by solving following equation dy by dx is equal to eta xy depending upon xi xy. This is an easy equation to solve, then do the given differential equation. If phi xy is equal to c is a solution of the above equation, we replace c by r and get r is equal to phi xy. To find the value of sxy, that is second canonical coordinate, we use r is equal to rxy to write y as a function of r and x. Then the value of sxy is obtained by the formula sxy is equal to integration of dx upon xi xy, which is function of r and x, and r is equal to rxy. Here the integral is evaluated with r being treated as constant. So by this way, we will find the value of r and s. Similarly, in the second case, if xi xy is equal to 0 and eta xy is not equal to 0, we find then r is equal to x and sxy is equal to integration dy by eta depending on r and y, where r is equal to x. These are the canonical coordinates in this case, when xi xy is equal to 0 and eta xy is not equal to 0. Now, once the canonical coordinates are found, then using canonical coordinates, the ODE y1 is equal to fxy is transformed into ds by dr is equal to omega r, or any other symbol you can use as a function of r. So here you can see when we are using the canonical coordinates, whatever the differential equation may be, it becomes in variable separable form. So now this, which can be solved easily using integration by formula s is equal to integration omega x del r is equal to c, where c is arbitrary constant. Therefore, the general solution of ODE is Sxy minus integration omega r del r is equal to C. Now, surprisingly, all the standard forms use the symmetry method. We'll see that all the first order order standard equation like linear equation, Bernoulli equation, homogeneous equation use symmetry technique. For these equations, the infinite symbols are as follows. The type, that is linear ODE, Bernoulli ODE, homogeneous ODE, and we know these are the standard forms of this. And it is calculated that infinite symbols for these equations are xi is equal to 0, eta is equal to e to the power minus integration px dx. For Bernoulli equation, xi is equal to 0, eta is equal to e to the power n minus 1 integration px dx into yn. And for homogeneous equation, psi is equal to x and eta is equal to y. So we can say that all the standard form ODE divided by dx is equal to 1 minus pi square upon xy plus 1, which is a non-linear equation and it is not fit in any standard form. We'll solve it by the symmetry method. Here we'll show that the infinite symbols are psi is equal to 1 by x and eta is equal to minus 5 by x squared. The canonical coordinates are r is equal to xy and s is equal to 1 upon 2x squared, which transform the given equation in ds by dr is equal to r upon r plus 1. But as you can see, this was the original equation, and using the canonical coordinates, this is transformed into variable separable form. Now, for these calculations, we have made a program or algorithm in Sagemath. For these programs, you should know the Python language and the concept of Lie symmetry. So you can also develop these types of algorithm. Here, you just see in this box, if you insert the right hand side of the equation, pi square minus 1 divided by x square y plus 1, that is the original equation, right hand side of the equation, we are getting tangent vector or infinite symbol xi and eta as 1 by x and comma minus y by x square. That is infinite symbols, we are directly getting output as xi is equal to 1 upon x and eta is equal to minus y by x square. And after finding this infinite symbol, we'll use again the algorithm to find the value of RMS. This algorithm searches infinite symbols or the given ODE from the set of 71,288 different pairs of xi and eta. But in some case, if the value of xi and eta is not found by this first algorithm, so then we have the second algorithm. In this case, again, when we'll give the inputs, we get the determining equation. And in this particular case, we equate the coefficient of y square, y cube, and y to the power 0 with respect to 0. We get the determining equation. And when we solve this determining equation, we get the value of infinite symbols as same as on solving differential equation. We get infinite symbol as xi is equal to 1 by x and eta is equal to minus 5 by x square. So I think either we'll get directly the value of infinite symbol by a first algorithm, or in case if we are not able to find, then we can use the second algorithm to find the value of psi and eta. And after this, we have made an algorithm to find the value of r.
Sir, screen is not visible.
Hello.
Screen is not visible, sir.
Screen is not visible.
Screen is visible.
Hello. Okay.
Sir, screen is visible. No issue over here.
Okay,
you can continue, sir. Please.
Thank you, sir. Okay. For finding the value of s, again we have made an algorithm. So using again here, if you put the inputs 1 by x and minus 1 upon x square, which we have calculated the value of psi and eta, we get the output as s is equal to 1 upon 2x square. That is, now we have found the value of RNS also. Now, these two values, RNS, will convert the given equation into variable separable form. For this also, we have made an algorithm. Here, if you put again the value of, when you solve the r is equal to xy and s is equal to 1 upon x square in terms of x and y, we get x is equal to root 2s and y is equal to r upon root 2s. When we put these two values and the right hand side of differential equation, we get t is equal to r upon r plus 1, where t is ds by dr is equal to r upon r plus 1. In this algorithm, I have used the symbol t for ds by dr. So you can see which is the form ds by dr, that is in variable separable form. And when we'll solve this, we get s is equal to r minus log r plus 1 plus c, because it is in variable separable form. So using integration, we can find this value where c is constant. And in terms of variable x and y, solution is given by again putting the value as and r in terms of xy. We get this exact solution. So here, using the symmetry method, we have found easily the exact solution of the differential equation first order, which was not in standard form. Now for the second order ODE, y double dash is equal to w x y y dash. The linearized symmetry condition is given by x2 is equal to y double dash minus w x y dash is equal to 0. This is written in the solved form, is equal to 0 whenever y double dash is equal to w x y dash, where x2 is given by xi del by del x, eta del by del y, eta 1 is equal to del y dash plus eta 2 del y double dash. And eta 1 is given by eta x, that is partial derivative of eta with respect to x, eta y minus xi x y dash minus xi y dash square. And eta 2 is given by this equation. Equating coefficient of various powers of pi dash to 0, we obtain the determining equation for finding infinitesimal xi and eta. So here also we'll use the linearized symmetry condition to find the infinitesimal xi and eta. Let us take an example. Solve the second order ODE y square is equal to y double dash plus 2x y dash cube is equal to 0, which is again a nonlinear equation. Now in this case, linearized symmetry condition is given by x2 y2 y double dash plus 2x y dash cube is equal to 0, when y double dash is equal to minus 2x by y dash cube upon pi square. That is, we first write this into linearized standard form like this, solved form. You can say it is written in the solved form. Then x2, when we will operate on this and we'll solve this, then value of x2 is xi del by del x, eta del by del y, eta 1 del by del y dash, eta 2 del y double dash. When we'll operate on this, we get this equation. On further solving, we get 2 xi y dash cube plus 2y eta y double dash plus eta x, eta y minus xi x y dash minus xi y dash square into 6y dash y square, and all these terms, this equation. Now next thing, we will have to substitute y double dash is equal to minus 2x y dash cube upon y square in the above equation, and we'll put all this equation and we'll do this calculation. We get this equation, and on further solving this, we get this equation 2 xi y square y dash cube minus 4x y eta y dash cube plus 6x y square eta x y dash cube, 6x y square eta y, and all this term. So this equation we get, and from this, to find the determining equation or infinitesimal xi and eta, we equate coefficient of various powers of pi dash to 0. So all this calculation we'll have to do for finding the value of xi and eta. For this purpose again, and we equate the value of pi dash 4 to the power 4 to 0, pi dash to the power 2 to 0, we get all this determining equation. So to avoid all this calculation, again we made an algorithm. Here you can see in this algorithm using the Python language and the concept. When we put the value here in this box, right hand side of differential equation, I have used the term b for y dash because there are some constant that in Python y dash is having some standard different meaning. So I use the b for y dash. If you put this value, then we are directly getting, without all this calculation which I explained in the last slides, we are getting the determining equation as we get output the determining equation which are same as we obtained by calculation above, that is minus xi xx plus 2 eta xi xy is equal to 0, and all these four equations. Now solving all this equation, we get the values of infinitesimal xi and eta. So when we actually solve this, we get the value of xi and eta. Xi is equal to 2c1y minus c2 upon y square x square plus 2 c6 y cube minus c7 upon y cube plus c8x plus c3 y square plus c4 y. Eta is equal to c1 y square plus c2 y x c5 y plus c6 y4 plus c7 y square, where c1 and c8 are constant. Now from here, x is equal to xi del by del x, eta del by del y, setting c2 is equal to 1 and all other constant to 0 in xi and eta, because these are the constant. We can take any constant as a 0 or 1. So we are in particular taking c2 is equal to 1 and all other constants are 0. We get x is equal to minus x2 x square upon y square del by del x plus x by y del by del y. And using the techniques explained in the previous slides, values of r is equal to x5. The value of x is s is equal to r square by 3x cube. When we put the value of r here, we get y square by 3x. Now for the further calculation, we solve r and s in terms of x and y. So solving r and s for x and y, we find that values of x and y in terms of r and s are x is equal to r square upon 3s to the power 1 by 3, y is equal to 3rs to the power 1 by 3. Now once this canonical variables are found, the equation is transformed into some other form. For this, we use the following formula to convert the given ODE in terms of r and s. dy by dx is equal to dry by drx, d2y by dx square is dr dy by dx upon drx, where dr is partial derivative d by dr plus s dash d by ds, s double dash d by ds. Then the second order ODE y double dash is equal to w x y dash is converted into dr dy by dx dr by x is equal to f r s dash, where what is s dash? S dash is partial derivative of s with respect to r, and f is independent of s. This is important. That is, the right hand side of f is independent of the s. Okay, again for this we have made a program, and again when we put the values over here, the value of x and y which we have calculated in terms of r and s, and the right hand side of the equation, we get the transform equation as v is equal to minus 2t by r, where v is second partial derivative of s, second derivative of s with respect to r, and t is equal to sr. So again, writing s double r for v and sr for t, we get the resulting equation as r into s double r plus 2 sr is equal to 0, which is second order equation independent of s. Now it is independent of s, so we can write t is equal to sr. We obtain r tr plus 2t is equal to 0. That is, writing in the usual form, that is del dt by dr is equal to minus 2t by r. So the second order equation is converted into first order equation, and also it is in the variable separable form. So which is ODE of order 1 in t and R. On solving easily, we can get the value T is equal to C by R square, that is ds by dr is equal to C by R square, where C is arbitrary constant. This is first order ODE in variable separable form. Again, this is the first order ODE in variable separable form, which is independent of S and can be solved by quadrature. By solving, we get S is equal to minus C by R plus D, where C and D are constant. Conversely, converting the above equation in xy, that is, S and R, we are going to convert now in terms of x and y using the relation R is equal to xy and S is equal to y square upon 3x. We get exact equation of the ODE as y square by 3x is equal to minus c upon yx plus d. So conclusion, this symmetry technique can be used to find solution of first order ODE which cannot be solved by no standard technique. Also, it can be used to reduce order of ODE of higher order. In this talk, I tried to introduce the symmetry method for solving ODE by considering first and second order ODE and some algorithm which have been prepared in open source Sagemath software. The method can be used via higher order ODE as well as for PDEs. That is, this can be used for higher order ODEs, and even we have applied it for the PDEs also successfully. For more details, one can refer the following books given in the reference. So these are the references. This is the book of Khare, Symmetry Analysis of Differential Equation and Introduction. This is Peter E. Hayden's book, Symmetry Method for Differential Equation. Third book is Blumen and Fumey's book, Symmetry and Differential Equation. This is Ruth A. Stenhouse. In this book, he has given many solved examples in detail, 4 to 5 examples. This is Rizwan's book for learning the stage, and this is State Osan's book for stage who are very new for the Sagemath and the Python. Thank you very much. Any questions from audience?
Any questions? Participants, if you have any questions, please you can note down your questions on chat box, on comment box, please. Any questions from participant side? You can write it in a comment box.
Okay, one question I can see here.
So there is one question.
How he decide the value of xi and eta? Okay, the value of xi and eta is found by solving the determining equations. When we solve the determining equation, we find the value of xi and eta. Okay.
Okay, thank you so much, sir. Any questions still? Any query from the participant sides? Please, you can get it clarified from our speaker. I think so, sir. No questions is still remaining from our participant sides. Okay, let me move further, sir. Thank you very much, sir, for your very nice presentation. I, Dr. Jemikas R. Surawala, on behalf of Department of Mathematics, C.B.Patel Computer College and J.N.M.Patel Science College, Bharthana, Surat, Gujarat, feel honored as a coordinator of this 2 days webinar on geodesics on unit sphere, a differential geometry approach and solution of ODE using Lie symmetry and open source Sagemath algorithm to invoke an official vote of thanks for the day and enter for 2 days of webinar. Let me go in the order of session conducted. First day was started with a session on Geodesics on Unit Sphere, a differential geometry approach by Honorable Resource Person, Dr. Jatinder Prajapati. Thank you very much, sir, for explaining how to apply a concept of differential geometry approach practically on geodesics on unit sphere through video. It was really very informative session. Thank you very much, sir, for spending the valuable time with us. On the second conducting day, I would like to thank hearty to our resource person, Mr. Vishwas Khare, for his fruitful and fantastic session. Sir has explained Lie symmetry technique very nicely to solve ordinary differential equation and how to solve it through using open source software Sagemath algorithm in very good manner. Thank you very much, sir, for being with us and sharing your knowledge with us. We were unconditionally supported by the Katha Vibhag Navnirman Mandal, our management, especially our President Sir, Shri Pankajbhai Gijubai Patel, and in-charge principal, Dr. Fayaz Alam Sheikh, for giving us an opportunity to organize this webinar. I wish to thank Shri Praveen Bhai Taylor, who always give us motivation to arrange such an academic activities. I extend my thanks to our faculty of Department of Mathematics, Mr. Parimal Patel and Mr. Shivam Khalashi, for the cooperation. The session would not have been easily managed if we did not have the technical support from Dr. Sagar Desai, Associate Professor, and Dr. Nilesh Limbacha, Assistant Professor from our Chemistry Department. We thank you both of them for giving the best technical support to us throughout these 2 days. I also take this opportunity to thank those people who have helped us directly or indirectly. Lastly, it is you, all the participants, who have voted the flights with us from the first day to the second day. The end is beautiful only if the journey was smooth. So we thank you all for your active participation. I would lastly say a few instructions about especially concern for the feedback form and certificates. Link of feedback form will be sent to your registered mail ID by today evening and certificates will be provided within 6 working days. Thank you very much. Stay safe. Let us together fight with Corona. Thank you very much once again. Thank you all.
Thank you.
We are now going to end our session. Thank you so much for your very nice cooperation to all. Thank you very much.